Other questions? All right. So with that said, let's not worry as much about that low-level kind of implementation and consider what more we can do with these things called arrays. If we start to get rid of the addresses and just know that we have sequence of characters or anything else in memory, and really at the end of the day, we have the ability to lay things out contiguously in memory, back to back to back to back like this. So here are then 8 boxes inside of which we can put anything. But we've kind of been cheating as humans for some time. When we had Stelios' name on the screen, all of us in this room just kind of glance up and you kind of absorb his name all in one fell swoop. But it turns out the computers are not quite as intuitive or as all-seeing as we are, where we can sort of take in the whole room visually. A computer can only look at one thing at a time. And so a better metaphor than a box like this for the locations that you have in your computer's memory would really be like 8 lockers in a school, where a computer, in order to look at the value in any of those boxes, actually has to do a bit of work and open the door to see what's inside. And you cannot, therefore, see all 8 locations simultaneously. So this is going to have very real-world implications, because now, if we want to start checking the length of a string or counting the number of things in an array or moving things around, we're going to have to do one thing at a time, whereas we humans might just kind of look at it and say, oh, sort these numbers in some intuitive way. And that actually is a good segue to a very different problem, which is that of sorting values. So for this, we have, say, the equivalent of 7 lockers up here now. And behind these doors, so to speak, is a whole bunch of numbers. So we'll transition away from characters and strings and just generalize it to numbers, because they're convenient to work with. And we have so many of them at our disposal. But I'd like to find one number in particular. So suppose that a computer were storing an array of numbers, a whole bunch of integers, back to back to back to back. Here's what they might look like. The doors are closed, though, so we need an algorithm for finding a number. Because the computer can't just look at it and say, there's your number there. The computer has to be more methodical, probably going from left to right, from right to left, starting in the middle, randomly opening them. We need an algorithm. So for that, we get one brave volunteer. Yeah, OK, come on down. What's your name? Kristen? Chrissy, come on down over this way. All right, so Chrissy, all you know is that there are 7 doors. Nice to meet you. Here on the screen. And using your finger, you should be able to just touch a door to open or unlock it, and we'll see what it is. And I would like you to find the number 50. Damn it. Okay, very good. I feel like we need a better prize than a stress ball for that, but very nicely done. And let me ask you, if we can, if you don't mind me putting the mic in your hand. Here you go. So what was your amazing algorithm for finding 50?
I just clicked on it.
OK, that's
it
great.
Nice.
OK, so good. So wonderfully effective. Let me go ahead and reveal. Actually, let's do this. So here's where you could have gone wrong. Any number of places. And let me ask the audience before we try one other example, what strikes you about these numbers? Anything in particular? They're all in order? Unordered, kind of random. Although the very astute might notice something. Or someone who watches too much TV. Yeah. Yes, thank you. The 2 of us watch a lot of Lost. So plus we had to add a 7th number, so we added ours. So they are actually in random orders. I just kind of shuffled them arbitrarily. They're not sorted from smallest to biggest. They're not sorted from biggest to smallest. There's really no pattern, because I really just did shuffle them up. And that's problematic, because even though Chrissy got lucky finding 50, or was just so good at finding 50, it might be hard to replicate that algorithm and find it every time unless you know a little something about the numbers behind the doors. And so we do know that in this next example. So in this next example, there are still 7 doors and still the same 7 numbers, but now they're sorted. And knowing that, does that change your approach?
Well, I guess if they're sorted like lowest to highest, then it would, because I would know it's closer to the end. But if I don't know how it's sorted, then I guess I wouldn't really know.
OK, good. So let me stipulate they're sorted from smallest to biggest. And let me propose that you again find us the number 50. Yeah, this is not working out very well. OK, that is very well done. OK, so congratulations. One sec. So you'll see, thank you. So you'll see just how much more efficient her second algorithm was when she leveraged that information. But in all seriousness, You could do better, especially for very large data sets, if you know something about the data. If you know that these numbers are sorted, you could, as Chrissy did very intuitively and very correctly, go to the very end knowing that that's the biggest number. It's probably all the way on the right. If she didn't know that and just knew that the numbers were sorted and did not know if 50 was a small number, a medium number, the largest number, just it was a number behind doors, what would a smart strategy be given that lesser information? Yeah, we can try that same divide and conquer approach we did in the very first class with the phone book, right, where we looked roughly in the middle because we know that the M's, give or take, would be in the middle. And then if we're looking for Mike Smith, whose name starts with an S, we know that he would be to the right. And so we would go to the right and then divide the problem in. Today is not going very well. So we would divide and conquer the problem again and again. And we can do that here. Even though it's not quite as visually engaging as a phone book, you can kind of go to the middle. And if Chrissy had opened that middle door and seen 16, you would know what. And actually, I can recreate this. I'm just going to refresh the screen. So in this case, we have the same doors. I know 50 somewhere. And I don't know where it is, but 16. Now I know it's to the right, as you proposed. So now I can essentially eliminate all these doors, not even worry about them. And indeed, if I open them, we can confirm that I don't need to waste any time actually searching them. Now I've got 3 doors. What would you propose we do next? Yeah, go in the middle again. So here, 42 is a great answer, but it's not the one we're looking for. And indeed, we can throw this half of the problem away and finally search the right half, which now has been whittled down to 1. And then we would find 50. And if I can reconstruct what would have been a great history in the first example, how well might Chrissy have done theoretically, or if we did this exercise again and again and again with the first example? If you don't know anything about the numbers, you can get lucky, as one might, by just choosing a door, and wow, that happens to be the number. But that's not going to happen all the time, most likely. And so you might have to just start, maybe at the beginning, no, no. No, maybe you can get clever and skip ahead. No, no. OK, eventually, you will find it if it's actually there. But if you don't know anything about the numbers, the best you can do is what's called brute force. Just brute force your way through the possibilities until you find the answer. But in the worst case, how many doors might I have to open to find the number 50 if I knew nothing about them? Yeah, so all 7, right? If n is the number of doors, it might take me as many as n steps. In this case, it was like n minus 1 or 6 steps. But in Chrissy's case, clearly, there's a really exciting lower bound, because if you do get lucky, it might only take you 1 step. So that's an interesting range to consider. The solution to your problem might take 1 step, or n steps, or any number in between. But the binary search that you proposed in the second approach, where you divide and conquer, recall that when we did that in the past, we had a very nice shape to the curve that we drew that described the efficiency of that algorithm. And we'll come back to that before long. But let's just, for clarity, formalize just what these 2 algorithms are. If I start from the left and go right, or start from the right and go left, following a line, we would call that linear search. And it can be written in any number of ways. I came up with this pseudocode. But again, any reasonable person could come up with an alternative one and say it too is linear search. These are not official definitions. And I wrote it as follows. For each element in array, if the element you're looking for return true. So this is a very concise way of saying for each element in the array, just look at it from left to right or right to left. If it's the one you're looking for, return true. I found the number 50, or whatever it actually is. Otherwise, return false at the very end. And notice the indentation. I unindented it, because only as the very, very last step do I return false if none of my iterations through the loop actually return true. So that would be linear search. Binary search, you have to be a little more verbose to explain it, perhaps. And there's many different ways to write this out. But this is very similar in spirit to something we saw before with Mike Smith in the phone book. So if we go ahead and look at the middle of the sorted array, just as you proposed, and if the element you're looking for is right there, go ahead and return true. I found 50. I got lucky. It was dead center in the middle of my array in one particular running of this program. Else, if the element is to the left, search the left half of the array. Else, if it's to the right, search the right half of the array. Otherwise, return false, because it's presumably not there. So this would be binary search. And even though it's more lines of code or pseudocode, it arguably should be a little faster. Right? Because of that dividing and conquering and throwing half of the problem away, the problem gets smaller much, much more quickly. All right. So with that said, it seems to be a very good thing that having things sorted for you is a very powerful ingredient to a problem, right? It takes more work, should have taken Chrissy more work, would take all of us in general more work to find a number using linear search than by using binary search. Much like it would have taken me forever to find Mike Smith flipping one phone page at a time versus using the divide and conquer where I found him much more quickly by dividing the problem in half and half and half again. So that invites the question, how do you get something sorted? Well, let me go ahead and pull up these things, which we happen not to use in this class. But elsewhere on campus, you might have these blue books. And at exam time, you might write your name in the class and all that on them. And we've kind of simplified. So this is a person whose last name starts with A, last name with person's name starts with B, C, and all the way to Z. But suppose that people finish at different times during the exam. And of course, like you're in the science center or wherever, everyone just starts handing them in. And they kind of come in like this. And then the TF's at the front of the room, or professor has to actually sort through these values. Well, what's this algorithm going to be that we actually use? If you've got a pile of exam books like this, all of them have a letter associated with them, how would we go about sorting these? What do I do? Compare two at a time. OK, so let me go ahead and pick up a couple here. And since I'm the only one that can see them, you should be able to see them on the overhead, thanks to Ian and Scully. So P and H. So H goes before P alphabetically. All right, now what do I do? Pick up another two? Pick up one. Yeah, so maybe just pick up one. And I happen to get N. So that goes in between H and P. So I can kind of slide it in. Now I picked up G. That goes before H. Now I picked up another one, E. That goes before G. So it's actually getting kind of easy. Uh-oh, U. This goes at the end after P. And so I can keep grabbing one at a time, F in this case, and then kind of insert it into its appropriate location. And we won't do this the whole way, because it's going to get tedious, and eventually I'm going to embarrass myself by getting one of the letters wrong. But that's an algorithm, right? For each book in the pile, pick it up, compare it to all of the elements you're already holding, and insert it into the appropriate location. And we can actually call that something. That's something called insertion sort, insofar as the emphasis of the algorithm is, thank you, on inserting letters, in this case, into their appropriate location. So with that said, are there other ways than that? Let's go ahead here, and we have enough stress balls to do just one more human demo here beyond these books. These numbers here, suppose we wanted to sort these. I have 8 stress balls, 8 pieces of paper. Can we get 8 other volunteers? So yes, right in back, 2, 3. Let's go farther back, 4. Can I go farther back? 5, 6, 7, and 8. Come on up. Oh, next time. Next time. All right, come on down. OK. What's your name?
Jerry.
Jerry. All right, great. If you want to go ahead and step in front of a board there.
Armar.
David.
Chris.
David. Frankie. Kaylin. Nolan. David.
Jay.
David. Matthew. David. OK. So this is statistically anomalous insofar as we're actually very excited to say in CS50 this semester, for the first time ever, we watch these numbers annually. We actually have 44% women in CS50 this year. So as you can see, none of my demonstrations are going correctly today, but trust in that data. So if each of you could stand behind one of the music stands here, hopefully I have counted out exactly 8 people. We have in front of you guys numbers. So go ahead and turn around the pieces of paper, which represent the numbers that we have on the board here if I got the same order right. So there's going to be a bunch of different ways we can sort these 8 values. So how do we go about doing this? Well, much like you proposed earlier, just pick up a pair of blue books and compare them. Why don't I try that same intuition? So 4 and 2, these numbers are obviously out of order. So what do I want to go ahead and do? Yeah, so I can go ahead and swap these. And now problem is solved, which is great. I've taken a bite out of the problem. Let me move on. 4 and 7, those look OK. 7 and 5, not OK. So what do I want to do here? Yeah, so I can swap those. Thank you. So 7 and 6, also out of order. Let's swap those. 7 and 8, that's good. 8 and 3, not incorrect. So if you want to go ahead and swap those. And 8 and 1, if you want to go ahead and swap those. So what was the net effect? Have I sorted this list of numbers? So obviously not, but I did improve it. And what's the most glaring example, perhaps, of the improvement in front of these? Yeah. 8 is now at the very end. So the biggest number, if you will, bubbled up to the end as though it was bigger and sort of bubbled up. So that's good, but there's still work to be done here. So I can, again, just try to fix these problems locally. Just pick up a couple of problems and try to solve it. So 2 and 4, we're good. 4 and 5, 5 and 6, 6 and 7. Ooh, 7 and 3, if you guys want to swap those. Wonderful. And then 7 and 1, we want to do it again. And now, do I need to bother comparing 7 and 8? Technically, no, right? Because if we know 8 made its way, now we can start cutting some corners, but correctly, just to shave some time off of the algorithm, make it a little more efficient. Good. So sorted now? No, so we have to keep doing this. And let me let you guys now execute this pairwise at a time. So here we go. 2, 4, 4, 5, 5, 6, 6, 3, 6, 1. And we can stop there because we know 7's in order. Now we do it again. 2 and 4, 4 and 5, 5 and 3, 5 and 1. Improved, good. And now next, 2 and 4, 4 and 3, 4 and 1. And then 2 and 3, 3 and 1. And then 2 and 1. OK, now it's sorted. Yes, very well done, very well done. So it's kind of tedious, frankly, and I didn't want to keep walking back and forth because thankfully we have like all of this manpower, these multiple CPUs, I guess literally today. So we have all of these CPUs or computers that are able to help me out, but it was still very slow. I mean, it's a long story. So let's rewind just once and do one more. If you guys could rearrange your pieces of paper so that it matches the screen again, just to reset to our original location. Let's go back there. And let's try one other approach. I've tried the insertion approach, whereby I just take a problem like the blue book and insert it into its correct location. But honestly, that was getting a little tedious, and that's why I aborted, because it's going to take me longer and longer and longer to find the right location among all of those blue books. So let me try just a more intuitive one. If I want to sort these numbers, let me just go and select the smallest number I see. OK, 4 at the moment is the smallest number I see, so I'm going to grab it for just now. Now, again, these are lockers, even though we humans can see them all. The computer can only see one location at a time, and this is indeed the smallest number I have seen thus far, so I'm going to grab it. Oh, but very quickly, I can abort that because now I found an even smaller number, so I'm going to hang on to that instead. 7, I'm not going to worry about that. 5, 6, 8, 3, 1. I found a smaller number. Now, I need to kind of do something with this. I want to grab the 1, so I could just put the 2 here. And what do I want to do now with the number 1? Yeah, I kind of just want to put it here. And so I can do this in a few different ways. But you know what? I'm just going to evict whoever's here, because it's a pretty low number, but it's also random. It could have been a big number. So let me just make room for it and do that. I have selected the smallest element. Is the list sorted? I mean, obviously not. But is it better? It is, right? Because the 1 is now at least in the right location. So I've solved 1/8 or 1/8 of the problem so far. So that's not bad. What could I do next? Let me apply the same algorithm. Let me select the smallest, which is currently this one, still this one, still this one. Nope, 3 is smaller. Oh, 2 is even smaller. So let me ultimately grab this. And you know what? 4, you really don't need to be there. I'm just going to evict you again and put 2 where it belongs and move this one over here. So now the list is even more sorted. And if I proceed to do this again and again, if you want to just keep handing me the smallest number, 3. OK, so I'm going to go ahead and just evict 7, because it's kind of a random number anyway. And now, thank you, 4. I'm going to go ahead and evict 5. Even though kind of feels like I'm making a little bit of work for myself, on average, it's not going to matter. Sometimes it'll be good. Sometimes it'll be bad. So let me go ahead and put 5 over here. Now I need to select the next smallest element, which happens to be 5. So we recovered pretty quickly, so I'm going to evict 6 over here. Now I'm going to look for the smallest element. Now it's indeed 6. I'm going to evict 8, put this over here. And now 7 is good, 8 is good, done. But it's still kind of a long story, right? Like I'm going back and forth looking for these numbers. But this would be what we'd call selection sort. So thank you all very much. If you'd like to keep your pieces of paper, you're welcome to. And let me give you, give you guys a stress ball as well, and a round of applause, if we could, for you guys, if you want to hand those out. So as before, let's see if we can apply. Oh, welcome back.